You can.
Okay. Well, thanks everyone for coming to the VHI Colloquium today. We're very lucky to have Kasia Rejzner visiting from the University of York, where she's a professor there. She's been doing some really beautiful work on the fundamental aspects of quantum field theory. So excited to hear from her today about algebraic structures in quantum field theory in the presence of a quantum reference frame. Thank you.
Thank you. Thank you very much for the invitation. It's great to be here. So let's get started. I will start with presenting a framework for foundations of quantum field theory, which I've been working in, which is algebraic quantum field theory. And then I will introduce the notion of quantum reference frames. I will not assume that you know much about quantum reference frames, but if you do, that's great. If you don't, I'm going to start from scratch. And then I want to discuss some examples where the two come together, so quantum field theory and quantum reference frames. Okay, well, let's get going. So algebraic quantum field theory, so that is, technically speaking, my field of research. And it's a framework to study quantum field theories mathematically. Goes back to Haag and Kastler in the 60s. They proposed the idea to think about a quantum field theory model as assignment of algebraic structures to regions of spacetime. So here we have, we initially thought about the Minkowski spacetime. So let's take Minkowski spacetime, say in 4D, and then to every bounded region, we assign the algebra of observables that can be measured in that region. And then there is a notion of subsystems. So if you have a larger region, you expect to measure more observables. So you have the inclusion of algebras. So that's the basic idea. And then there are some properties that this assignment should fulfill, which are motivated physically, which were formulated as a set of axioms. So that's an axiomatic framework. And there are two that I actually care about, at least for the purpose of this talk. So the first one is causality. So that's a very fundamental feature of quantum field theory, that this is relativistic. So it has to mirror the principle that nothing moves faster than light, and in particular information. So if you have observables that you measure in two regions that are space-like separated, then you expect that they don't know anything about each other, so the corresponding operators should commute. Hence this axiom. So for two space-like separated regions, there is the commutation of the corresponding algebras. Okay, so that's one. And another one has something to do with dynamics, with time evolution, and this is also going to be important in what follows. So so if you in classical field theory, usually talk about initial data, you think about solving some differential equations, say in GR. That's quite an involved problem of nonlinear differential equations of hyperbolic type. You usually specify initial data on the Cauchy surface, where you have something like position and momenta, and then you can reconstruct the solutions in the whole space. Now, I want something similar to be true also for the quantum theory, so for these algebras of observables. So if I know my operators, my observables in a thin time slice in the neighborhood of Cauchy surface, then I want to say that, well, I know everything about these operators in the future and the past too. There is some sort of time evolution. Hence, so if n is the neighborhood of a Cauchy surface in O, then the algebras of n and O are exactly equal. So there would be an inclusion from the previous property, but here there is actual equality. Okay, so that's it. So that is how this was formulated in the 60s. There were a bunch more axioms that are maybe not so important here. Here's a picture of a black hole. That is, I guess, not the one I have on the merge. It's Great. I mean, I was really excited when this picture came out, because then you finally can put it in your presentation and not some silly simulation of how it's supposed to look like. But yeah, well, this motivates doing quantum field theory on curved spacetime, because not everything is Minkowski. There are wonderful things which are not. So yeah, black hole spacetimes, cosmological spacetimes, completely generic random spacetimes. And yeah, we should better be able to understand quantum field theory on that. And so this was something that sort of came about in late 90s, early 2000s in our community. People thought about generalizations and essentially replaced Minkowski spacetime with, well, a nice Lorentzian manifold and some properties for that niceness. But then the idea is the same. So you assign algebras to regions and you impose the same axioms. Okay, and a big breakthrough in the community was to show that this can be done in a covariant way. And that was the beginning of locally covariant QFT. And I should mention the paper of Brunetti, Frenhag, and Verch, where they made it systematic. Okay, so we do curved spacetime. But that's still not everything we need. So one of the criticisms against algebraic quantum field theory, which I think is quite reasonable, is that the original formulation in terms of operator algebras, Fewster and Verch algebras, is very beautiful. However, it's very difficult to construct models in 4 dimensions that satisfy all the proposed axioms. So you can prove a lot mathematically, but you of course want to describe reality too. Whereas quantum field theory typically works with perturbative methods. So that was the motivation for another development in my field, which is perturbative algebraic quantum field theory, where we eventually gave up on this strict requirement of having Fewster and Verch algebras, and we went to something more general. Yes, please.
So is the idea that if you get this algebra, you know everything?
Well, depends on what you mean by everything, because I mean, you also need, so if you want to connect to experiment, then you also need to know a state, right? So algebra, I mean.
But you've defined it there, or not? You have to say something more about states?
Well, so the state tells you about the particular measurement setup, right? So let's say, yeah, you can say.
Do you then need to do more work to find what the representation is?
Well, states are equivalent to representations, yeah. So given, given the algebra, you can already talk about representations, yeah.
You can talk about the
yeah.
But what's the point? What would amount to having solved the problem? You find the algebra and you say what the representation is? Or
so for me, like a full solution of the problem would be to specify the algebra and to have a classification of representations. So I know what's the vacuum state, I know what are the thermal states. So some sort of classification of the representations is, that's the full.
The algebra, it's a pretty big algebra, it has all the observable.
Yeah.
That doesn't generate all the states? I would thought that theory would be one or the
No, it's, yeah, so the problem is that, okay, so you can have some redundancy, you can have a pretty large center in that algebra, which is related to superselection sectors. So that's part of that classification. Yeah, so I think the practical issue with this is that you want to be able to identify states.
Sorry, you don't have superselection sectors in finite volume.
Oh, I'm not doing finite volume.
Oh, I thought you had a finite region.
Oh, no.
You're also taking some limit where that goes to.
That's correct. Yeah. So you have so you have those subregions. You assign algebras of subregions, and then you have like inductive limit, which gives you the full algebra. So yeah. So you have also like A of M of the whole space now. So that's yeah. So that's the full information.
So it's not just finding an algebra, it's finding an algebra that are limiting.
Yeah. so that limit you get from the net. So you have this assignment for larger and larger regions.
Is that limit unique, or
Sorry?
is there any reason to think that limit's unique?
Well, up to isomorphism. Like, I mean, so you do it essentially. Yeah, it's an inductive limit, so it is unique up to isomorphism, given the net. But yeah, I mean, coming back to the state. So I think the issue with non-perturbative AQFT is that you can pretty easily give an algebra of a sister algebra of observables in any interacting QFT in 4 dimensions. I can do it on the board. Now, but that's not the full solution of the problem, because the full solution of the problem would be also to identify, say, here is the vacuum state and KMS state, but like the vacuum is pretty fundamental. So what's missing in the non-perturbative setting is the construction of a vacuum state, because states exist on sister algebras, like plenty. That's not a problem. But physically, I'm interested in particular states that talk about, given physical situation. And this is something which we don't have in 4 dimensions non-perturbatively for interacting theories.
You have to construct a norm or not?
For a sister algebra, but as I said, I mean, the norm is not a problem. Like the biggest problem is to have distinguished states. That's the technical issue, and that actually is very easy perturbative. I mean, not very easy, but it's very well understood.
So there's one question on Zoom quickly. So Jacob Barrendes asks, does all this assume we are working in the Heisenberg picture? If we are ultimately interested in questions of measurement, how do we accommodate open system, non-unitary evolution, decoherence, etc.?
Okay, this is a great question. So I'm going to touch upon it a bit. I'm going to say a few words about measurement. And yes, we are working in the Heisenberg picture. However, a lot of these questions are answered when you specify states and the actual measurement theory. So there is a measurement theory on top of it, which I'm actually going to briefly discuss. But I won't discuss all of it because that is a topic for another topic. But that's a great question. Thank you.
You said 4 dimensions over and over again. Is it a problem that is unique to 4 dimensions? Like if it's higher, it's easier, lower, it's easier?
There are some problems which are unique to 4, because 4 is kind of critical dimension for, say, if you do statistical quantization or randomization group flow methods, then things are really bad at 4. Now, 2 is very easy, actually. 3 is okay. People do 3 plus epsilon or 4 minus epsilon. But 4 is, for some reason, particularly bad. Because, in many approaches, it's not just, particular. Oh, wow. Okay. No, it's finally gone. The problem has just gone away. Okay, yeah, so these perturbative methods, well, they essentially come from path integral. So like a very sort of, traditional formulation of quantum field theory, because, the path integral is a way to construct a state, in particular the vacuum state. Okay. So let me just say a few words about perturbative AQFT. So again, I'm a very algebraic person. I want to think in terms of algebras. And one way to construct algebras, given, say, classical theory, to construct a quantum theory, is using deformation quantization. There was a bunch of people who worked on that in our community, some combination of names, Brunetti, Ditch, and Frenhagen. And then there's another piece which is related to renormalization, because renormalization is needed to construct interacting QFTs, unless they're super normalizable, but that's not the case in 4D, at least for the ones I'm interested in. And this goes back to Epstein and Glaser, and it's actually quite old, but was a bit underutilized. All right, and somehow embarrassingly, gauge theories came a bit later, so there was a work of Stefan Holland in 2008, and there was my work with Hagen in 2011 that essentially solved the issue. And I have a review if you're interested. But yeah, so this is a sort of bridge between this algebraic framework and perturbative methods, which you can keep in mind if you want to put some models behind the abstract nonsense I'm going to talk about. All right, moving on. All right, so that is all very nice. I mean, QFT on curved spacetime is already somewhat in the direction of quantum gravity, and I'm sure that many of you are working on quantum gravity. It's a problem which is very fascinating. Initially, right, the way that people approached it was, well, Feynman already wanted to do it, right? So let's take some background metric, let's say Minkowski, take a perturbation, this is a field, let's quantize it, we're good. And that didn't work because, well, there was the non-renormalizability, which actually can be fixed in some ways, but there were other problems which are still there. A lot of methods in QFT work Euclidean signature. There are different features in Lorentzian signature, so one should keep that in mind when quantizing gravity. Background independence is a big one. Construction of gauge invariant observables, and the fact that when you quantize gravity, I claim, I think that is true, you need to go beyond locality, and quantum field theory tends to work with locality as a fundamental concept, so one has to give that up to some extent. Okay, so from my perspective, the questions that I want to address maybe in this talk is the construction of observables and this locality versus non-locality, and I want to convince you that quantum reference frames somehow come into this game. Okay, so if you want to read on more, well, I mean, there are two papers which are somewhat relevant. So this one with Brunetti and Hagen from 2016, when we worked on construction of observables. I might mention it at the end of this talk. And there is a more recent one where with D'Angelo, Drago, and Pinamonti, where we looked at renormalization group methods and renormalization group equations for gravity in Lorentzian signature. Okay. So this is kind of motivation in the background, and this is, yes?
When you say gauge invariant observables, you mean like perturbative or non-perturbative?
No, well, I mean, I'm a simple person, so perturbative. Okay, so, I mean, abstractly, right? I mean, in the end, I want non-perturbative. I want non-perturbative diff-invariant observables. What I can construct is perturbative diff-invariant observables. But yeah, in principle, at the end of the day, we want non-perturbative. Yes?
Why would we expect a problem with locality and perturbation?
Maybe not in perturbation theory, but yeah, I mean, I can construct these observables that are local at every order in perturbation theory. But I mean, at the end of the day, you know, if I was able to sum up that series, they wouldn't be local. So yeah, the problem is, yeah. Then just conceptually. Okay, measurement. So measurement was already mentioned in one of the questions, and this is another embarrassment that, you know, in this framework, we're working on foundations of quantum field theory for a long time, but only very recently people formulated a really robust measurement framework. And this is due to my dear friends Chris Fewster and Rainer Pfeff. Yeah, it's, well, I think it's very simple in a way, but also, yeah, one has to absorb a little bit of background. So I'm not going to give it justice, I'm afraid, because I have only one slide, and Chris Fewster would give a whole talk about it. So if he hasn't spoken in that seminar yet, then you have an opportunity to invite him. So I'm just going to give you a cartoon version, and I would refer you to this paper in Communications in Mathematical Physics from 2020 for the details. So here is the picture. So what are we doing here? So I have a setup where I have the system and the probe. The system is described by some net of algebras A, and the probe is some net of algebras B, and they are coupled in some compact region K. This is where they talk to each other. And there is another net of algebras C, which is the coupled theory, where the coupling is localized here. There is also the uncoupled theory, where we just tensor them together. They don't know anything about each other. Now, one of the axioms I mentioned at the beginning was the time slice axiom, which means that if I have a Cauchy surface, say in the future of that region, take its neighborhood, then any of these nets would, I would be able to reconstruct it from knowing the operators in that neighborhood. The same goes for the past. I could pick up a Cauchy surface here and the neighborhood, and I would be able to reconstruct the whole algebra. Okay, so from that, when picking up this Cauchy surface and this Cauchy surface, I have some identifications between coupled and uncoupled theory. Because here and here, away from the coupling zone, we don't know about the coupling, so we can identify the theories in the far future and in the far past. It's a bit like the scattering setup. So you can think about these theories to be independent, sort of not interacting with each other in the far future, in the far past. Something happens in the middle. And this identification, actually these maps, the future one and past one, in a sense, they know about what happens in the middle. So I said scattering, it is actually related to scattering, so these would be related to Miller maps, scattering maps, and the S matrix in practice. Okay, but so I'm going to use this identification to say that, well, I can prepare my probe in the past, so this is what I can do. I prepare my experiment. I pick two states, one for the probe, one for the system, and they are uncorrelated in the far past. And then I evolve them into the future using this scattering map. And then I measure in the future. So I'm going to measure some observable here in the future region. So there's some observable B, which I can now evolve back in time and see what was it doing where both of them were coupled. So yeah, I prepare early and measure late. And then, well, using these scattering maps, I can, well, essentially write down the expectation value of this probe observable corresponding to a particular induced system observable. So I can look at the expectation value of this probe observable for the state that I evolved from the past using these scattering maps, and then I trace out the probe, and then left with the component coming from the system. Yeah, so you can essentially read out information about the state of some induced system observable using conditional expectations of the probe observable in the future. Yes?
And does the wave function collapse?
That's a very good question, and I do refer you to, there's a very nice review article of Rainer and Chris where they address it in more detail. So in a sense, this is about state update rules. So their measurement framework tells you what are the state update rules. And there is a very beautiful result. Do you know the Sorkin impossible measurement problem? So this is something due to Raphael Sorkin, who pointed out the potential issue with measurement in QFT is that if you have three regions, so A and B, which are causally disjoint, but you have intermediate region which has some overlap with the future of the 1A and some overlap with the past of region B, then there is a risk that you can pass information through that region. Okay, so that would be the impossible measurement, because then you propagate information faster than light, and that problem is avoided in this measurement frame. So that's one thing. I mean, about the collapse, I don't want to make So in a sense, you don't need to talk about wave function and it collapsing, but the problem with faster than light propagation of information is avoided. So, yes. I don't know who was first.
So I'm a little confused about the pre-coupling region and the post-coupling region. So does this mean sort of related? Does this mean that no entanglement?
Yeah, so correct, because you choose, in the pre-coupling region, you choose states that are uncorrelated, right? You take a tensor product. But then when you evolve it through this, then things could happen. So there could be entanglement at the end after they interact. So,
So that's allowed?
Yeah, that's allowed.
Just a quick question.
Yeah.
Are you allowed to make real-time measurements? It seems like you're doing some asymptotic thing where you exist, where you assume there are.
No, that doesn't have to be asymptotic. No, that's, I mean, by real time, you don't mean that the time is real. You just mean non-asymptotic, right? Yeah.
The tau plus, I see. So you're just saying that you are only allowed to
so this
measure
could be,
after coupling.
Yeah, so this is happening at a finite time after the coupling, so this is all finite time. I think that's first. Yes. Oh, I'm going to explain it in the next slide. Yeah. Okay, that is the next slide too. Okay. Sorry about that. You had a question.
Maybe we can save this for the end.
Yeah.
And you might get to this in the second hour of your lecture.
Yeah, exactly.
But I'm just curious where Bell's theorem fits into all this.
Oh, these are great questions. Again, Chris has a recent paper which might address it. So I'm very happy to discuss about that. So you can describe things like the Bell scenario using this framework too.
I just want to know where that fit in.
Yeah. No, I can give you references. I think it's the recent paper that discusses it, or just something he told me. But there is existent framework to do it. So yes.
So just so my understanding is that Sorkin's impossible measurement protocol would appear to give a protocol whereby the von Neumann measurement could cause superluminal signaling in quantum field theory, right?
Yeah.
And this is proposed to circumvent that.
Yeah.
Uh-huh. Do you believe that, or do you? I'm not super familiar with Sorkin's the details of Sorkin's argument. Do you agree that his protocol would allow for superluminal measurement or superluminal signaling if von Neumann measurement is your measurement model?
So I think the key point is that it would require non-local coupling in this intermediate region. So it is not it is not possible in this measurement because this measurement works with the coupling of local QFTs, which is in turn also local. So I think, but however, if you would have a non-local intermediate theory happening in that coupling region. That would create an impossible measurement. But that would also not fit into this protocol. So yeah, I think it's really locality versus non-locality, and I think it's very subtle.
The von Neumann measurement is definitely non-local. So.
Yeah. But again, yeah, I think that's the reason why it doesn't work this way. Yeah. Okay, symmetries. Right. So I hope I will answer your question. So let's say we have a space-time with some symmetries. So let's say Minkowski, Schwarzschilder, whatever you have in mind, and that your quantum field theories respect that symmetry. But the coupling region doesn't. So the coupling region is a compact region you choose arbitrarily, and then let's say if your background spacetime is Minkowski and you translate your region in time by time translation, which is a legit symmetry, you are clearly in a different region. So you can think about moving your experimental setup somewhere else or performing it at a different time. And this is a different measurement. It's a related measurement, right? So you know exactly how to go from one to the other. So the measurement scheme is covariant, but it's definitely not invariant because you go somewhere else. The same goes for these algebras of observables. They are covariant. We know how things transform, but they are not invariant typically under these symmetries. Okay. So we have covariant theory, covariant measurement, and now the question is, well, so how are we going to A, get something invariant out of that, B, well, clearly because the theories are covariant, they are not going to provide a labeling system for those measurements. There isn't an intrinsic way to say, I'm at point X in space-time. I need some way to specify what X is using, using what. So this is where the notion of a reference frame is coming in. It's not new and it's not really quantum. I mean, reference frames are something that we encounter already in mechanics 1 or mechanics 0. Because in order to talk about positions and time in terms of numbers, we really do need some rods and clocks, and we are kind of used to it. So there's nothing surprising. But it is more tricky if you want this to come intrinsically from a quantum theory. And, if we believe that the world is quantum, and even worse, if you want to quantize gravity and describe everything intrinsically in terms of that, well, then this reference frame would also have to come from something quantum. This is where this theory of quantum reference frames comes in, and yeah, well, I'm not going to quantize gravity because we only have like 20 minutes.
Yeah, you have an extra
Okay. give me an extra hour. But yeah, at least I want to give you a flavor of what sort of observables and what sort of concepts might be useful if you want to after the talk. Right. So here is the general idea. So I have my quantum field theory together with the measurement scheme. Everything sits inside of some algebra AS as per system, and then I have some labeling system that allows me to fix this extra symmetry. So if my symmetry is time translation, this would be a clock. And this is, again, some algebra of operators, AR, and I'm interested in invariance. So my symmetry group acts on both AS and AR. Then I'm looking at invariance. This is the problem I want to solve. Yes?
Is this AR different than the AB from the previous slide?
Yeah, so both of them, so the coupled, uncoupled, they all sit now in AS. So everything from the previous slide sits here, and this is an extra rods and clogs system that fixes, so that tells me where the coupling zone is, essentially. Right? Because what was not given by my measurement scheme was to specify the position of this coupling. But this is something which is covariant under the symmetry. But I want to say that, well, it's 11:36 when I measure, then I need a clock. And this clock is sitting in AR. Alrighty, yes?
So why do we need to worry about all this, and why couldn't we just talk about it? Is that not?
I mean, we could. I guess, again, well, the S matrix is very global, I think. I mean, if you're only interested in scattering experiments and sort of like asymptotic to asymptotic, yeah, you can. Yeah. Yeah.
But some people would argue that those are the only things, right? That there aren't local.
Well, but they can go and measure something in the lab. Like there, I think.
Most labs don't have structural activity.
Well, that's yeah. Is that the problem with funding? They should. I mean, if I was to set one up, just have one on the orbit of a black hole, that would be fascinating. I think it's fair, and I grew up as a quantum field theorist, so I think it's fair. However, I'm now at this crossover with quantum information and kind of maybe somewhere between QFT and quantum mechanics. People are interested in local, or at least sort of semi-local measurements and observables. And I think this particular setup was a bit missing in quantum field theory, because quantum field theory was always focused on scattering experiments. So I think it's just interesting avenue to explore, especially because at the end of the day, I really am interested in things like relational observables for quantum gravity, which are exactly of that type.
Okay, but
yeah.
There's a logical possibility that those can't be defined, right?
But the relational observables for quantum gravity.
Well, with the local observables, yeah.
No, I think local observables are never, well, I don't know, it's true. Local observables are never going to be diff invariant, right? Yeah. So, but this kind of things, so the guys here are the relational observables, or in other words, dressed observables. So even in QED, that's somewhat more understood, right? So you can think of like a dressed electron, right? The dressed electron is a semi-local observable, right? Because of the photons, of course. And this sits in here. And this comes, in a sense, you can think of this dressing as a quantum reference frame, and you think about this dressed observable as coming from this setup. So I think it's an interesting way of identifying non-local observables in QFT and quantum gravity in a systematic way. Okay. Right, so here is a definition, because I'm a mathematician, so I should give you a definition at some point. Yeah, so there are many notions of quantum reference frames. So there is perspectival, perspective neutral, and operational are the main ones. I am in the operational crowd because, yeah, I find the definition most appealing. So what's a QRF? QRF is going to be the following data. There is a Hilbert space. There is a positive operator valued measure. Note that I don't require projection valued measure, so it's not the PVM, it's POVM. So this is, yeah, somewhat weaker. And this, so G is my symmetry group. And then this labeling space, sigma, is the quotient of that by some closed subgroup. You can make it trivial if you want. So yeah, so this provides labels for my measurements. And there is some a strongly continuous unitary representation of G on my Hilbert space. And there is a compatibility between that representation and the natural action of G on this labeling space. So we want this sort of stuff. Okay, so that's it. Now, there's some nomenclature. So if we happen to have a PVM, we say that our QRF is sharp, otherwise it's called unsharp. And if H happens to be compact, it's super nice, and it's called compactly stabilized. Yes?
In quantum theory, this would just does this contain more than a choice of coordinate system?
Does it contain more? Well, in a sense, yeah, it is a choice of coordinate system. Yeah. It's not, yeah, I mean, it doesn't even have to come from quantum field theory. Like, this data could come, say, from like dust fields or just quantum mechanical system. So, but yeah, it is like choice of coordinate. In the interest of time, I might skip some of the more technical stuff, but I can answer questions later. So I'm just gonna, yes, this is about compactly stabilized, but let me just talk about an example. Here is a simple example that I think if that wouldn't work, then we would be doing something completely hopeless. The particle on the line. So here the Hilbert space is obviously L2 of R. You have this POVM, which is given essentially you multiply your wave function by characteristic functions of intervals. And then you have this unitary representation of translations by momentum operator, right? So you position the momentum operators. And then the fun stuff is that this compatibility condition between this representation and just a shift, right? This is equivalent to saying that the commutator of X and P is I, which is quite nice. So that's the sort of motivating example. There is one more, which somewhat relevant for quantum mechanics, which is about unsharp time observable. Well, we cannot have sharp time observables because some no-go theorems, but we can do something which is second best. So there is a nice construction, which is called compression by projection. So given a sharp QRF, you can apply some projection to your POVM, and you project your Hilbert space, and then you get the compressed QRF, which is well, not sharp anymore, but we don't worry. And there is a nice result saying that all the nice QRFs arise this way. There is also an arrow the other direction. In particular, this can be used to construct unsharp time observables, and yeah, then I think there are two examples I want to mention. So one comes from a paper of Chandrasekaran, Longo, Penington and Witten, where you would use like position operator on R+. So there the projection is happening in the energy representation, and this just go R to R+. And more generally in quantum field theory, people were using this framework without knowing, constructing time of occurrence observables. There's a paper to that extent. But yeah, it's a tool which has many uses. Okay, let me mention some more interesting examples, which I've been working on with my collaborators. So my motivation to actually look into it at all was this paper I already mentioned, CIPW, from 2023, about QFT on the sitter spacetime, or actually on the sitter static patch coupled to an observer, and the type change of von Neumann algebras. And I like von Neumann algebras, so of course I like it. But then I wanted to understand how that fits with the idea of quantum reference frame because that clock looked very much like a quantum reference frame. So that was the motivation for the paper which we have with Fewster, Janssen, Loveridge, and Waldron, where we generalized that setup using more sort of universal notion of quantum reference frames and symmetries, which can work beyond, obviously, de Sitter spacetime, like anything with a symmetry. So yeah, so that kind of covers the idea of QRF as another quantum system, could be even quantum mechanical. Now, more recently, I've always been interested in boundary things. So you can look at the setup where you say have a diamond, and you have, for example, QED inside the diamond and on the boundary of the diamond and on the corner, and use the corner degrees of freedom as your quantum reference frame. And this is what I mentioned before. You can construct rest observables this way. And you can also do it asymptotically, which I think is very nice. Still work in progress, but will be out soon. And finally, that was also somehow mentioned in the room, dynamical coordinate fields, and that is related to my old paper with Brunetti and Frenhagen, but I really want to do it more QRF style now that I'm 10 years wiser. Okay, so these are the examples, and let me, okay, so I have two choices. So I can have like 5 minutes to describe the details of the first example or the last example. And yeah, what's the feeling from the crowd? So I can talk about types of Neumann algebras or dynamical coordinate fields.
Whatever you're most excited about.
Oh, well, I'm always excited about new stuff. So I will talk about the first one because that's a newer paper. Everybody knows about von Neumann algebras? Yay! Yeah. No. Okay. So von Neumann algebras are a really great tool. One of the great things about von Neumann algebras is that there is a nice classification that was, well, many people worked on it, but Alancon did quite a lot of progress in that regard. Yeah, so we model in AQFT sort of proper, non-perturbatively, we model local algebras as von Neumann algebras. And yeah, there are different types which correspond to different physical situations. So in quantum mechanics, when we have qubits, we have something called type 1n, so essentially matrices. Great. Then if we have infinitely many degrees of freedom in the QM system, then it's one infinity. In quantum statistical mechanics, we have typically sort of limits of matrix algebras. These are, the nice ones are of type 2-1, it's also type 2 infinity. And in quantum field theory, we have type 3, which is actually the nastiest one. And yeah, so why am I being so judgmental? Well, some of it is related to the existence of traces, and this is a black hole seminar, so probably, you know, computing entropies of black holes is of interest. And computing entanglement entropy when you have a type 3 situation is difficult because the only meaningful concept is relative entropy, because otherwise things go ahead and explode. So you have to either regularize or you do relative entropy. Yes?
Isn't quantum statistical mechanics like just related to QFT bioelectric fusion?
No. Well, it depends. Okay. Depends what you mean by that. So, because the Wick rotation is something that happens on the level of, well, state and representation and particular computations. Here, I really want to go a step before that and talk about the algebras of operators. So I don't think it's that straightforward. I mean, And also, the big rotation is a very subtle thing because it changes, like, it's an analytical continuation. So it changes the analytic properties very drastically. So yeah, I guess, you know, if you squint your eyes, you can probably, you know, do that relation for particular systems. But yeah, that thing changes because this badness of type 3 is really related to, like, in UV divergences, infinities, randomization. And this is, yeah, this just doesn't go away.
In quantum statistical mechanics, you use statistical mechanics of like quantum systems with finite degrees of freedom.
Well, with countable. This is more like continuum situation. Yeah, yeah, yes.
My question was related.
Yeah.
To clarify what you mean by quantum stack.
Yeah,
It's
yeah,
not like
yeah.
statistical field theory. But
No. That would live here. Yeah. Right. So that, you know, that could be a problem, or this could be an opportunity. So yeah, what to do with type 3, and yeah, well, one thing that was raised and that was discussed by Witten in the context of quantum gravity, and in that paper I mentioned, was that, well, maybe we are looking at it wrong. Maybe just looking at the net of algebras is not enough. And I completely agree. It's probably not enough. So if we think about measurement seriously, and if you think about this whole setup together with the measurement and together with, say, a reference frame, well, that whole setup is going to lead to a different algebraic structure. And that was demonstrated in this paper of Chandrasekaran, Longo, Penington, and Witten in the example of this. So that was the motivating piece. Okay, and how this fits into the viewpoint I'm presenting? Well, we think about this clock, this observer as a quantum reference frame, and then measurements on this de Sitter static patch are formulated in this local measurement scheme I described. Okay, so if you don't like what you see here, you can also look at another formulation of quantum reference frame by a bunch of colleagues in Okinawa and formerly in Waterloo, which, well, I mean, it's a slightly different perspective, and I think it's worth to have a look as well. Yeah, so I think maybe points that are worth mentioning about our approach is that, well, in this paper of Chandrasekaran, Longo, Penington, and Witten, they really care about the diffeomorphism constraint. So this is all tied to the diffeomorphism symmetry. In particular, what we are looking at is more, general in the sense of it's just about symmetries. It doesn't have to be diffeomorphism, just about symmetries. It's about, so the fact that measurements are local is one of the ingredients. And thermal properties is another important ingredient. So we try to explain sort of mathematically and a bit physically why do you get type 2 from type 3. So the first step, you get type 2 infinity just from the fact that you have local measurements and that you have a thermal in the KMS state of your quantum fields. So that's item 1. But that's not super great because that only admits a semi-finite trace. You want a finite trace. And that is actually coming from thermal properties of the quantum reference frame. So that was our new observation. So if a quantum reference frame also admits, well, not a state because the normalization issues, but if it admits a thermal weight, which is almost as good as a state, for the same as your quantum field, so they're thermalizing, then you really obtain type 2-1. So somehow this compatibility between thermal properties of QFT and a QRF gives you the desired result. And I think there might be something more to it. Okay, I think maybe it's the time for me to wrap up, and I can answer, this is the other topic, questions later. So thank you very much for your attention. Oh, this is these are the papers. So the one I talked about and the older one on dynamical coordinates. So if you're interested. Yes. You were first.
So if I understood correctly, the last thing you said was that if your measurement apparatus can thermalize, then you get a type 2-1 algebra?
Yeah. If it admits this thermal state or a thermal weight more generally. It was actually very fun. So that was something which was pointed out by my postdoc Dan Janssen, that the kind of like we had some sort of condition that was necessary for 2-1, and that this very naturally corresponded to the thermal properties of the QRF.
So I wanted to ask you about just so in the last slide that you had displayed, talking about your viewpoint. So just to understand the viewpoint, do you have, so when you're defining a quantum field theory, the quantum field theory does not have observables, but observables are only defined relative to some reference frame. So
right. So I think too many things are called observables.
Okay.
So what we call observables in AQFT, right? These are these local observables, these local operators.
Okay.
Yeah, and then but how do you observe them? So in order to observe your observables, then you need, well, you might want to introduce some operational viewpoint. So if you introduce the measurement and the QRF, then you arrive at those relational observables. So then these describe relations between my local operators and the quantum operators in my quantum reference frame.
And the type of algebra of those relational observers can be weaker than the...
Or can be the same. I mean, this is not necessarily happening. And I want to argue that if I want to talk about diffeomorphism invariant observables for quantum gravity, well then I would introduce dynamical coordinates, which again come from another quantum system. And then my observables would also be relational. They would describe relations between some local observables that themselves are not physical in quantum gravity, sort of aspirationally. I don't know who was first. I think
Does the last slide you showed, does it imply that your choice of like a reference frame somehow imposing like a UV cutoff on the EFT or something like that?
That's an interesting viewpoint. Let me see. Can we make that precise? Okay, so in a sense, yes, because the way I think about it is in quantum geometry. So if you think about non-commutative geometry, was this idea, right, that the spacetime is not commutative and this mollifies the UV divergences. That is actually not too far from that, because my quantum coordinates, they're a bit unsharp, right, because they are coming from the quantum system, and that unsharpness introduces essentially some smearing, some mollifying of those UV divergences. So the fact that they have a quantum system is what makes it better. That's how I see it. Yes?
I think I have two questions, but I'll just have, maybe I can ask one first. You mentioned there are those relational observables that you have constructed. Would you comment on its relationship with those observers that proposed direct and unroot?
Yeah. Well, like So you're thinking about like en-route Witt detectors, or
that kind of thing.
Yeah, it is right. I mean, en-route Witt detector is a very simple, like, two-level system. So, I mean, I guess you can think of it as, well, I'm not sure. Yeah. I mean, okay, I think if you stretch it, then maybe.
That wouldn't give you the geometry you were with.
No, that's right. That's right. So I think one thing is you need a sufficient resolution, so to say. So like one of this compactly stabilized condition. There's a additional property we require is that this labeling space is good enough to describe what you're labeling, right? So that your QRF has sufficient resolution to, say, resolve time or position space. So that en-route Witt detector wouldn't have that property. So we wouldn't have enough resolution. And I think, yeah, then there is no hope that it provides this sort of smearing. Yeah. Yes.
To measurement analysis from
Yes.
the perspective neutral perspective, like perspective neutral approach.
Yeah.
So like.
Oh yeah, that's the other one. Yes.
Yeah. So like I think like usually in the setup of perspective neutral approach, like you impose time translation.
Yeah.
As a gauge constant.
Yeah.
To the whole system.
Yeah.
Which in this case is QRT. And like the measurement process.
Yeah.
But on the other hand, the QRT itself has another time translation invariance, which is a global symmetry. So in that sense, like you have like two concepts of time in this kind of setup. Like how do you reconcile like these two different concepts of time in that case, and how they're like mathematically related? Yeah,
that's true. So one of the technical differences between our approaches is that in the perspective neutral, you have this constraint and you impose it on the level of Hilbert space representation by some averaging procedure. This is the step we don't do. So we are constructing, they are perspective neutral and we are Hilbert space neutral. We are constructing these algebras sort of kind of a bit independent of a particular Hilbert space representation. And we don't do that averaging. I don't like that averaging because like it's very, I mean, technically it may or may not work and usually it doesn't. So as a mathematician, I'm a bit nervous about it. But yeah, so I think that the reason why there is this discrepancy is that there is an extra step that's being taken in perspective neutral approach that we don't take. And that's why we don't see the same issue. Yeah.
I think we are past time. There's a question on Zoom, but I think we should probably close at this point. Yeah. Thanks.